EORI Insights is a quarterly series meeting that provides a platform for EORI to report on Institute project work, and also a platform to present proven and emerging technologies to be presented to the public, that these technologies may have application in Wyoming oil and gas fields. This will be about an hour-long presentation today. And so we'll hold questions until the end, if that's okay with everybody. And then we're going to make a copy of this presentation, not only the PowerPoint, but also the video. That'll be online with EORI's website, which is right here on the bottom corner of the slide. And today, I'd like to introduce Dr. Geoffrey Thyne and Teresa Nealon from ESal. Dr. Thyne started his career with Arco Oil and Gas as a research geochemist in Plano, Texas. He received his PhD from the University of Wyoming in 1991, after which he went to teach at the California State University at Bakersfield, and then later at the Colorado School of Mines. Dr. Thyne returned to the University of Wyoming in 2006 and co-founded ESal in 2013. I'd also like to introduce Teresa Nealon. She earned both her Bachelor of Science degree in Mineral Engineering and Mathematics and Geophysics, and a master's degree in Hydrology from the Colorado School of Mines. Teresa has 25 years of experience in business and project management, and most recently served as the director of the Wyoming Carbon Capture and Storage Technology Institute at the University of Wyoming. Teresa is also a co-founder of ESal. So with that, I would like to turn it over to our speakers today. Thanks, Teresa.
Good morning, everyone. Thank you for being here. And thank you, Lon, for the opportunity to speak to this illustrious group, both here and online. I'm going to give a presentation today that's much more business focused than technology focused. But don't worry, if you have some technology based questions, I've got the CTO here and he'll be happy to answer any of those for you. So I wanted to start off by talking about, whoops, can we get that off of there? There, oh. The unparalleled value of engineered salinity, ESal. And sorry, as I figure out how I'm going to use my glasses here today, because you're all now blurry, but I can read the screen. Our technology is a field-proven technology that increases oil production by engineering the salinity of the injection water. So there's no chemicals used. It's simply working with the injection water chemistry. And it is a low-cost technology. So we're looking at 50 cents to $2 a barrel, which if you look at other competing innovative technologies that are 10, 20, maybe even 50 or $60 a barrel, it's quite a value. We get rapid response in 6 to 9 months. So when you start injecting the engineered salinity injection water, after you flush the reservoir, one pore volume through the reservoir, then you're going to start to see your results. It is also very effective in increasing oil production. We're looking at 5 to 15% of the OOIP. And once we do a test pilot at your field, and it is effective and shows results, then you can go ahead and increase your reserves. So you go to the SEC, you increase your reserves, and that really improves the financial picture of your company. So you're either setting yourself up for a nice retirement, or you've got money to do your next business venture. There's little or no change to infrastructure, so you're not building a pipeline, you're not worried about doing permits, you're using the same people, the same processes, and the same equipment. And finally, there's no field damage. So you don't have to worry about, deploying this in your field and am I going to affect my production down the road? No, in fact, this technology will actually reduce reservoir scaling. So the workflow is 20 times faster and 40 times less expensive than industry standard. So I think it's easy to say that it's the simplest and lowest cost technique to improve oil recovery in the market today. So let's talk a little bit about who we are. ESal was founded in 2013. It is a Wyoming company. It's run by Wyomingites, Geoffrey, Thyne, and myself. And we have gone through the path that a lot of innovative entrepreneurial ventures go through. We got the NSF funding, phase 1 and phase 2, as well as the state match. So we were able to really develop the R&D into a viable business enterprise. You can see who our customers are there, some of them. I'm sure you'll recognize a lot of names. Some of them, unfortunately, have been purchased by other companies, so it's not up to date as far as who's bought whom. And we're considered the world leader, or maybe perhaps I should say we consider ourselves the world leader in wettability measurements because we've performed more than 5,000 in the lab, and I don't think anybody else in the world can say that. So we really have a good grasp of wettability. So if we look at ESal's wettability cliff notes, so these are the main points, and Jeff can talk for hours about all the science behind it, but I want to talk about the takeaways that, if you remember, you'll be well down the road to talking to anybody about wettability and how you can use it in your reservoir. So if we look at the graph on the left, it's showing the points for reservoirs, the data for the reservoirs that we've either measured in the lab or that were found in the literature. And any reservoir will be found on that graph because it encompasses all the types of wettability that you would see, which is oil wet, neutral wet, and water wet. So that's on the x-axis, and on the y-axis, we have residual oil saturation. So obviously, when you're an oil producer, you want your oil saturation to be low because that means you're producing more of the oil. And if you notice, the lowest oil saturation that we see on there is at neutral wettability. And so some fields with native neutral wettability would be fields like the East Texas oil field, Ekofisk, Prudhoe Bay, Gwar in Saudi Arabia. So these are the big, huge producers that have been producing since the beginning when they were drilled. They're at neutral wettability. They're naturally at neutral wettability, so they're big producers. So what we've discovered is that obviously most hydrocarbon recovery is at neutral wettability, but our lever is that we've determined and been able to quantify and find a predictable way to take oil wet reservoirs on the left, if we look at this graph, and water wet reservoirs on the right in the blue, and move those wettability values from either oil wet or water wet to neutral wettability via salinity. So the idea is therefore to move the reservoirs to neutral wettability, and that will only work in reservoirs where they have sensitivity to salinity, because that's our lever. Other companies might have a different technology lever. They may use a different parameter. Ours is salinity. So the method is practical, predictable, fast, and inexpensive. And let's look a little bit at our process. So what we do is we take the rock, water, oil, and field parameters that a customer would provide, and we put them into our screening algorithm, and we get a score between 0 and 100. And I'll go into this a little bit more when I get to the Wyoming fields. If we have a good to excellent score, then we say, okay, we should probably move on to the detailed lab analysis. And this is where we measure the wettability of the customer's field. So they give us the water, rock, and oil, actual samples from their field. And we do a modified flotation experiment and determine what the wettability is of their field, whether it's oil, water, or neutral wet, and is it sensitive to salinity changes? If it is, then we can do some more analysis that will tell us what is the recipe for the injection water so that we can move their water or oil wettability down to neutral wettability. We run economic models and we can tell them exactly how many barrels of oil in addition that we can produce for them with our technology. So let's look at some examples of work that we've done for clients. This one is a company that was working in the San Andres ESal, and their injected water was putting their reservoir at water wet wettability, and we were able to do our detailed laboratory analysis and recommend a new injection water chemistry so that they increase their oil production by 31%. And in this case, although it's not shown on here, they also drastically reduced their produced water. Another client was working in a Gulf of Mexico sandstone field. We had worked with this particular champion at a different company in the past, and he went to his new company and said, hey, I think we should talk to ESal. They were originally producing, their original wettability in primary was a very great condition where you're at neutral wettability, so they were getting good oil recovery, but then they had to move on to EOR, phase, secondary production, and so they wanted to do water flooding, and they were using seawater. And so this gentleman said, hey, I think we should get with ESal, and they came to us, and we said, no, you don't want to use seawater. I know it gives you a lower OpEx, but you're really affecting your recovery. So we had them use produced water, and they had a 10 to 15% increase in recovery. And you can see the number of barrels there. And this example is one in which the customer came to us and said, we have 7 fields, and we just, for some reason, they weren't sure why, because people, there's turnover at all these big companies. We changed the water flood chemistry in these 7 fields. They're all in the Williston Basin and in the Coral Creek anticline. And 6 of them did well and 1 of them did poorly. We don't understand what happened. Can you explain it to us? So we did our work on all fields, and I'm just giving you an example here of one that went very well. And you can see on what we call the smiley face curve, that U-shaped curve that I've been talking about all morning, that they moved their oil wet field to more neutral wet. And you can see in the decline curve that they actually moved the decline curve so that the rate decreased. They got an additional 12.5 years of production and many, many more millions of barrels of oil as well as dollars. And if you notice the costs there, both CapEx and OpEx, less than $2 a barrel. Then we looked at the field where they didn't have good production. And they had moved from their nice, almost neutral wet condition in the smiley face graph and the green point up to the red point. So they went more water wet than neutral wettability. So they kind of locked those oil barrels in the reservoir. So their decline rate increased greatly. They lost 23.5 years of production and left many millions of barrels in the ground. The nice thing about this is if they went back to their original, injection water chemistry, they could unlock those barrels out of the ground. They would be able to produce those. So this is probably a novel concept in this industry, but we guarantee our results. We're not going to work on marginal fields. If we do the screen and you've got a marginal or not recommended field, you'll see those scores in a minute when I go into the Wyoming cases. We're not interested in doing that work. We only want to work on the fields where we can make a difference. So we guarantee our results. If a client comes to us now, we say, let us look at your entire portfolio, screen your entire portfolio, and where it makes sense, we'll do our deployment of our technology in your field and we'll guarantee the results. We don't make money unless you make money. And this chart here gives you an idea of how accurate our technology is, where it makes sense. Obviously, the reservoir has to be amenable to salinity changes. Otherwise, our lever doesn't work and we can't help you out. So let's talk a little bit about Wyoming. And let's go into the screening a little bit more. So we take the rock, water, oil, and field data. So in the rock, we want to know, what kind of, is it a sandstone, a carbonate, how much clay, the water, various parameters, including the TDS. In the field, we're interested in things like the original oil in place And the temperature, the oil, we're interested in the API, the TAN, the TBN. So, you know, there's over 20 parameters under those 4 categories that we look at. We input them into our algorithm. And in this case, we obviously didn't get 100 fields worth of data from customers, but we went in and got the publicly available data and put it through our screen. And you can see we have a not recommended, a marginal, an average, a good, and an excellent rating that will come out of the screen to tell us whether or not this field looks like it's going to be amenable to our technology. And if you look good to excellent in the green, we've got about half the fields. Half of the 100 fields that had publicly available data are amenable to our technology. So if we extrapolate that to the entire state, there's a good chance that our technology will work. So what we went with, or what we went to, is we decided to take some of the big fields. If you notice the percent of Wyoming OOIP, there's 10%, almost 10%, 9%. So these are the big 8 fields in the state, and they are amenable to our technology. And you can see our recovery of 5 to 15% will get many, many millions of barrels of oil. In fact, our technology can reach the same 2 billion barrels that the CO2 EOR can go after, but we don't have pipelines, we don't have permits, we don't have to wait for all of that, and we don't have the CapEx that you have with CO2 EOR either. So we've got a nice production of millions of barrels, and you can see at $50 a barrel what that would equate to for the state and its producers. So in closing, let me say that we offer an unsurpassed technology with a guarantee that you won't find anywhere else in the industry. We stand behind it because we don't make money unless you make money. 5 to 15% additional recovery, very low cost, 50 cents to $2 a barrel, rapid response time, and it's proven in the field. You're not going to be the first to try it. So give us a call, or check out our website and contact us that way, and we'd be happy to talk to you about how we can help in your field. Any questions?
What's a mechanism that reduces your residual oil saturation? Water, it's not more water.
And you'll need to come up here, Jeff, so that you're near the microphone. Oh, no, but I meant for Jeff to come and answer the question.
Sorry.
So you want to get down to
Yeah, like why? What is intuitively?
intuitively you go,
Why do you think that you're?
no, yeah, you say no way.
This advances the slides.
So I came prepared for questions. I want to go back to this diagram, and this is really what you're asking.
Yeah.
How does this work? And it took longer than I thought to figure it out. So that's some of the data that was shown before. This is from publications. This is what happens when you add in actual fields. Those before were water floods from core floods. Okay, so core flooding. Here's some field data. This is mostly North Sea, follows the same curve. So the question I had to ask myself was, this is happening, right? I mean, there's too much data. It really happens. I didn't find it in the textbooks, darn it, because that would have made it easy. So why? Well, wettability is another word for relative permeability. So what we're doing is we're shifting the rel perm curve, or we're shifting the capillarity of the reservoir. And I wanted to amplify the remark Teresa made, where she said you needed a pore volume to get this. You get this as soon as the salinity front sweeps the reservoir. So you can go a whole pore volume, but you're going to get the response injector to producer time. So that's the 6 to 9 months. All right. And most of the fields, all the data she showed you, none of that is a full field sweep. Just to clarify that. So how does it actually work? This is what we all learned in school, right? That picture up at the top. Wettability is water wet, the water sticks to the rock and the oil sits in the middle of the pore, and then vice versa. And then they had this mixed wet, and these are cartoons, but nonetheless, this is what we all have in our mind. And what we do as engineers is we change the rel-perm curves to reflect the state up above. And we usually do that through core floods, and we get special core flood analysis, SCALs, and we get our rel-perm curves. And then you're done, right? As an engineer, you're done. So I was shocked to realize we could change the rel-perm curve in the reservoir with water chemistry. That was pretty crazy. So how? Sorry, I have some, I threw in every slide I could think of because I knew the questions would come up. These are some of the examples Teresa mentioned of large, naturally neutral wet fields. And they all hit 50% recovery. And then this was the one that was weird. So I'm at the Institute, and one of my colleagues is doing the TARIS database, I think it is, and recovery, right, by DOE. And there's this one point way out here on the end at 75% recovery. And I went, okay, I'm a geologist. So I go, oh, okay, that's bullshit. Pardon my French. I don't have to be nice now. When you teach, you have to be nice, okay? But here I don't. And so I went and looked it up. East Texas oil field. Who knew? Drilled in the 30s, nice sandstone, 4,000 or 5,000 feet down to 10-acre spacings after 70 years of production, only re-injecting produced water. Now at 85% recovery. Whoa. So that was, sorry to differentiate there, but that was interesting. To get to your question, this is what wettability actually is. And it's back in the literature, way back. Well, not so much for me. In the 60s, these guys were talking about what they call Dalmatian or spotted wettability. So it's not that picture that we all have. Instead, what it is are little speckles, and that's oil sticking to a quartz overgrowth in this picture. And why is it sticking there? I mean, quartz is water-like, and yet oil sticks to it, and it doesn't stick like a smooth coating. It's little patches. Zoomed in here, same picture. These droplets of oil. What's going on? Well, very nice Russian lady did some work a few years ago. Went in, this is a carbonate, washed it, SOx will extract it, right? All the oil's gone. No, she found little patches of organic material stuck on the rock. That organic patch is oil wet as far as oil is concerned. Some of them come off, some of them don't. And so all the salinity is doing, if we stop for a second, we imagine that reservoir, we have oil, water, rock. They're in chemical equilibrium before we drill. Some of that oil is surfactant, polar compounds. We all know this, and sometimes you can use alkali to change the surfactant concentration in the water by taking the natural surfactant out of the oil and putting it into the water. But when you put it into the water, it also partitions onto the rock, creating these little patches. That's what actually changes the wettability. So why doesn't it work everywhere? Because sometimes the oil doesn't have enough natural surfactant in it. And even when you change the salinity, which changes the partitioning of these natural surfactants out of the oil, into the water, onto the rock, or back the other way, apparently, because you go from oil wet reservoirs to neutral wet. That's how it's actually happening. So it's a different picture of wettability. And suddenly, in a lot of Wyoming fields, at least, you have a tool you can change the wettability or the rel perm of your reservoir rock. So we're not working, most people with surfactants, chemical EOR, we talk about lowering the interfacial tension between oil and water. We're talking about taking it on and off the rock. We essentially Teflon coat the rock. So now when oil's trying to flow through that pore throat, instead of a water wet pore throat where you have resistance, capillary resistance to the oil moving through, you've put some speckles, if you will, onto that pore throat, and there's much, much less resistance to oil flow. So that's how it actually works. It's just something that's not in the textbooks yet. Is that, sorry for a long.
You have to have full core. What do you have to do for the final, for the lab test?
Cuttings. So one of the big things was, you know how hard it is to get core. And I know someplace, I've been told, there is a core warehouse up in the powder full of core, but no one knows where it is. Right? It's the mythical warehouse, and it's got core from all the formations, producing formations, but I couldn't get that. No, so we went with cuttings. Because that way, everybody's got cuttings, maybe coating the road, but, but nonetheless, we can dig them up and clean them. So we get cuttings and we grind them up. This has to, maybe I don't know if I can go back. Ooh.
Yes, the other arrow below it.
The other arrow, yeah. That would be smart, but nah. No other arrow. So we grind the cuttings up. They have to be silt size, the grains. You saw a tube in there. There we go. So each of, this is like crazy. This was an LSU PhD who did this. So there's rock, water, and oil up at the top in this test tube. You shake them up really good. And I thought nothing would happen. The student called me up and she goes, "Oh no, I did it 50 times. A bunch of rock floated." I said, "Rock does not float." Okay. What is the density of the rock?
Yeah.
Closer to the.
You need to move closer to the mic.
Density of the rock's about 2.2, 2.6, right? But a bunch of the rock was entrained in the oil. If the grains are small enough and the force of the oil sticking to the rock, it floats. It's oil wet for all intents and purposes. So we took 1,000 samples to make this work in the real world with real oils and all that kind of thing. But that's the cuttings. So we take the cuttings, grind them up. There's 1 million grains. I didn't believe this. There's 1 million grains in a gram of rock when you grind it to that size. Unbelievable. So you're testing 1 million surfaces at once in every test tube. This is a salinity series. Salinity changes in these 8 test tubes. It's in triplicate. You can't see that, but this way we do it in triplicate. So essentially 24 samples per rack. And so you've tested 24 million grains across 8 salinities, one of which is the reservoir salinity. We go higher, we go lower, and you get a curve. And you put it on that U-shaped curve, you get the answers, put it on the U-shaped curve, bam, you got your answer.
What are you measuring? What are you physically measuring on the curve? How much is floating?
Yes, or how much sinks. It's much easier to weigh the sinking afterwards. You try and suck the floating off, it's like, ooh, it's really gross. We have done that, by the way, just to see what floated and what sunk. Like in a sandstone, you'd go, well, what's floating, what's sinking? Sandstone, it's everything, but clay dominated for floating. The scary part's the carbonates. Half of it floats and half of it sinks. I mean, depending on the salinity. And we have looked at the grains. I mean, we're using a sieve, so we got a range of grain sizes. And we can't find any difference between what floats and what sinks. So you just get enough of those little speckles on your rock, and now it's oil wet, and it's going to partition physically into that oil phase. So simple very accurate test using a four-place balance. So you use gravimetric was the number. And then you got a little formula that translates it into wettability numbers. That's the Amont scale that you guys saw earlier. And bam, you get your answer. Hence the guarantee part, because, well, actually the guarantee came because of the field data. When I saw how close we came to predicting actual field scale results, I was baffled. If any of you have done EOR, done core flooding, it's all about scaling in terms of taking the test results and scaling them up to a field. Really hard to do. When I did core floods with CO2, I could get 100% of the oil out of the core, right? But when we went to the field, what is it? 8 to 15% roughly of additional production that you get. But this scaled up exactly. The only answer I have, anybody asks, is there's 24 million grain surfaces, and it must just be reasonably representative of the reservoir. Doesn't go so well like in some reservoirs where you have a lot of stratification of lithologies, because then you've got to test multiple lithology. But carbonates are wonderful. Carbonates are what our carbonate rock pore throat's made out of, right? Carbonate. You get into sandstones, then you get into, that pore throat, is it clay? Is it carbonate? Is it framework grain, feldspar and quartz? So it's a little spongier in sandstone. And it's also in sandstone, it's not as uniform a mineralogic distribution. But nonetheless, we've done sandstones and they come out pretty close.
So you're measuring you're determining the wettability with the oil, when the oil's the rock's floating with the oil. That's
Correct.
telling you it's oil wet.
Repeat that.
I'm sorry. Can you repeat?
When that-
No, you repeat it for him so the people on Zoom can hear.
with that-
I'm sorry, I'm
We're-
trying to help the
we're-
people on Zoom
We're
here.
gonna go again. Ask your question, please, sir.
So when you grind it up and you have rock floating with oil, is that telling you that it's oil wet?
Yes, the question is, when we grind that rock up and mix it up, stir it up real well, and it floats, quote, that is oil wet rock. Absolutely.
And then you've got to determine how to get it neutral.
Correct. So that was, he wants to know, how do we get it to neutral? So the 8 different salinities gives us a curve, if you will, salinity versus wettability. And what we're looking for is, does that wettability, where does it start in the reservoir? And then as the salinity changes, which is what we can change in the field, right? We can't do much to the rock or oil. Does it move toward neutral? How much does it move toward neutral? And that gives you, luckily, the number of barrels, additional barrels. If we knew the OOIP accurately, okay, to start with, and that's your information that you guys have all got about your fields, we can say, oh, we'll get this much more. Translate that into barrels, translate that into dollars.
So what if the water or the reservoir is water wet?
What if the reservoir is water wet? Then hopefully changing salinity will move it toward neutral wet.
So then you're gonna start getting rock floating with the oil as you change it? Or not?
Yes. So in other words, if you started out all water wet in this test, all the rock would be in the bottom.
Right.
And then as you change salinity and some starts floating, you got a lever. And that's your big knob that you can twist. And if you went and tested that rock with a core flood, you would see different rel perm curves. And just as an aside to all the old people in the industry, they never did many of those tests using formation water. They made something up in the lab, and it was usually sodium chloride solution. So they may, even the rel perm curves that they got may be, oh, that may not be exactly right.
With some of our water floods, you know, we started out injecting produced water and then we started supplementing with fresh water. So we've changed some salinities in our reservoirs and our water floods. So this would be interesting to see how that affects the reservoir when we add fresh water to our injection.
Absolutely. So the question is, or the comment is really, the standard practice is we start out our water flow with produced water because we have lots of it. But pretty quickly we get to the point we have to supplement, and we normally do that with fresh water. And we are going to change the wettability at that point in the reservoir by this injection of this fresher water. It could be good, it could be bad. And you saw the example there where it was bad. And that's the same, the only difference in that field, that is the Cedar Creek anticline, actually.
Oh. okay.
Cedar Creek anticline, 7, that's a old shell play. 12 fields, 5 are still in primary, 7 are in water flood. They do not know why the engineer changed to fresh water. They can't find the engineer anymore. Too many changes, right? So it was a Denbury engineer, and he decided to flood the 7 fields, which they were using produced water at about 75 to 90,000 TDS. He changed it all to 5,000 TDS and did not re-inject the brine that's gradually being shoved out. They're at about half a pore volume at the point that you saw. They don't know why he did it. He may have read some papers at the time. This is like 2005, low salinity water flooding was pretty hot back then. So maybe that's why he did it, but it worked in 6 of the fields to some degree. The 7th field, boom, was that one. And the only difference we could see was the oil chemistry changes along the anticline. There's some biodegradation and stuff. So it's very sensitive. The answer or the reflection in the field is very sensitive to the oil chemistry.
So we've got 3 questions online, actually. The first one from Eric Robertson is asking, can ESal technology be used with CO2 water alternating gas projects?
Hey, Eric, good to hear from you. Sorry, I know him, as many of you do. Yes, these are different mechanisms. So it is possible we can synergistically work in the water leg with CO2 WAG.
The next question, actually, we're going to have a 2-parter from Lisa Wolf. What are the differences in this process with different API oils? For example, she was wondering about the Uinta's waxy oils.
Great question. There is some, how can I put it? There is some variation based on the oil chemistry, absolutely. We've only done one waxy Uinta oil, and within the practical range of salinity variation in the field that they could implement, there wasn't a big response. But it's not really the API is a reflection, but it's how much surfactant, natural surfactant you've got in the oil that you can move in and out of the oil and stick on the rock.
The other part of her question is, what is the process or workflow of working with ESal?
That would be getting in touch with us, talking to us about your field. We would sign a contract for the nominal fee to do the screening. It's $25,000 for up to 10 fields. So you would provide us with, as many of the 20 parameters for our screening tool that you have. And we would run that and see if you're coming out at a good or excellent level. If it is good or excellent and you want to proceed on to the detailed laboratory analysis, that's $75,000 per well. And then if that turns out to be, amenable, if the reservoir is amenable to salinity change, then we go into the deployment, and that is by purchasing a license, and the amount of the license would depend on the size of the field and the number of the wells there. But we find that the cost benefit ratios are so extreme that we have latitude to work with the financial situation at your company and work things out that way.
Thank you.
Suggestion,
Yes.
Teresa, when you compare to CO2, different technologies, you might highlight the fact that once you inject CO2 on the clock, unless you're going to change all the tubulars to stainless steel, you're going to eat your field tubulars, no matter how much corrosion resistance treatment you try to. So just to highlight economic one, patience over time. Question number 2 would be, with regard to agents, we talk about adjusting salinity, produced water, and if you come up short of salinity, how do you handle it? I'm looking at your graphs. Okay, I have produced water in polymer, and I can reinject it. It's a silty, people call it silty sand, which is a misnomer in the first place. It's a silty shale. It's tight. And so if we come up short with produced water, what do you use for an agent?
I got that.
Okay.
It's a good question, and it's same in all water. It could go all the way from unconventional shales, which we worked on, all the way to water floods in an old field. Okay, you found out you needed a certain salinity. Where are you going to get it? There are 2 answers to that. The first is water treatment on site, skid mounted units. They're expensive. I would not immediately suggest that as the first choice, but it's economics. The major choice is to find a second source of water that you're going to mix with your produced water. Wyoming is very fortunate that we have stacked reservoirs in most fields, and the salinity of that water will vary with depth. So we have found 1 or 2 cases already, and Teresa alluded to the fact that the public data we use for the 100 fields, that all came from the Institute. So thank you, Institute. And we have found 1 or 2 cases where if you take the water from reservoir A and inject it into C and vice versa, you actually get the benefit. So what we suggest economically, and based on our experience with various customers, is they usually just set up a big mixing tank, right? And a lot of people have old wells on the field, alluded to with freshwater wells. You drill down to the Fort Union or whatever, right, to get your makeup water.
Fox Hills, Muddy, Meadows.
Bingo. So if you've got old wells, which Denbury did up in the old shell fields, is they just squeezed a lower zone, came up, perfed, and turned those into water wells for supply wells. And they did 1 per field or 2 per field, and then just replumbed some stuff. Because they're just re-injecting all this salty produced water. They're just getting rid of it. It just depends. Every answer is unique. So, but most people just find a mixing tank, not much in the way of CapEx, and go ahead and mix their produced water with whatever. Are you getting fresher or are you getting saltier? So that's the short answer for where you get your water.
Sensors, monitoring, and
Oh, I don't think anybody's gotten that sophisticated. But absolutely you could automate the whole process, right? Because all you need is a conductivity meter. You're just looking for a certain conductivity. One person got very interested in manipulating the balance of calcium and sodium, things like that. That gets more expensive though. So it's always an economic choice of what do you need and what can I do to get it?
Jeff or Teresa, can you talk about how the guarantee works? At what level? So you do the 25,000 screening for 10 fields. I would think that's not a guaranteed thing. You're going to screen.
Correct.
For the screening.
Correct.
If it looks good,
Right.
you're gonna move forward for the 75,000
For the lab analysis,
tests.
right, which was all those little test tubes that he pointed
Right.
out. Yep.
And then if that looks good and the operator agrees to move forward, from that point forward is where this guarantee would kick in?
Correct,
And
correct,
that's based on the license that you would purchase?
correct. And they don't pay us unless we give them what we tell them we'll get them at the start.
And that license fee, you said, depends on.
The size of the field, the number of the well, and the number of the wells in the field, so it
Okay, what if
varies.
an operator only has one field and they don't need screening for 10?
Then they pay the 25,000, it's just up to 10, yeah,
That's up to 10,
yep, up to 10,
1 to 10.
yes, exactly.
So in this case, if that was the decision, we're gonna move forward with ESal, and you get that kind of result at that point, the guarantee would have kicked in.
Yes,
How does that work?
yes, they would not pay us, so when, you got a licensing
The
fee,
license fee.
yep, you would not pay us.
I think you had another question from.
Yeah, we've got another from online. We've got Matthew Johnson, who asks, how sensitive are your results to the heterogeneity in the reservoir? For example, the varying mineralogy, clay content, capillary detail, and how do you handle that heterogeneity in your practical field deployments?
This is the question, and I'm assuming this is aimed at sandstones, Matt, so I mean, carbonates tend to be a carbonate unit in Wyoming, Madison, right? It's pretty uniform. For the sandstones, we sit down, we work with the field geologists, the company geologists, and we say, how much heterogeneity do you think you have? And so I direct everybody, for instance, muddy sandstone. If you did miss Steve's talk on Friday, I'm sorry. It was really good. Should do it again, Steve. But muddy tends to be pretty heterogeneous. So we design for the centroid, if you will, what the company agrees is the average unit that they want to produce out of. And there may be, if you get more clay, for instance, it gets clayer, is that a word? More clay rich. There we go, that's correct. More clay rich, then you're going to have a little different result. But we can look at that in the lab. We can change if what's happened before. I'm thinking of a particular example in Wyoming. I won't say any more than there's an upper and lower unit. And the lower unit is more clay rich, lower permeability. So we just tested both and said, oh, look, it's pretty much the same. You're going to get maybe a little better sweep actually in the clay rich unit and not quite as good a sweep, enhanced sweep in the sand rich unit. But don't worry, the sand rich unit is where they got all the oil out of anyway, up to this point. So they may want to come back and do that lower unit. And this also works to how much are you going to work over the field once you have this lever? Do you want to change your perforations a little bit? Do you want to squeeze? Do you want to drill a new well? I mean, it's basically just giving the engineer a new tool set that they're going to employ.
So looking at this, they've lost barrels there. Your technology should be able to fix that.
Oh, yeah.
Right?
Yep.
So, but they haven't. Employed you?
Can we tell the story of Shell being bought by Denbury, being bought
No,
by Exxon?
Denbury being bought by Shell,
Oh, no,
being bought by Exxon.
no, it was Shell. And then Denbury
Oh.
bought from Shell. And then Denbury, we remember, was exciting. And Denbury wanted those fields for CO2 sequestration in the Q45. Exxon bought them and now they're for sale again. So if the ball ever stops, rolling on the roulette wheel, we might talk to somebody who would go, oh, wait a minute, we can get a whole bunch more money out of this one field. So that's why they haven't done it.
Probably might be back in again.
Yeah, who knows? I mean, it's the case in many of the last 10 years in the business.
It's been tough.
It's who owns this now?
And yeah,
Have you done anything with the slick water fracs?
Slickwater fracs. Yes. This was a really interesting question. So it's unconventional, obviously. you have to be a little sensitive when you're fracking in the sense of they've got a chemical mix already. And if you're going to change the salinity, it's going to change the efficiency of that chemical mix. So you got to work with somebody who's willing to say, okay, well, test that. So our last customer, for instance, hot shotted us the surfactant mix that they were using on a Sunday. So I have to go to work on a Sunday and test it both straight water change and then water change with all the chemicals in it. And so that's usually how you handle it. That was the case where they got 20 or 30% more oil. They switched over and it was a test. I'll put it that way. Although they did 10 wells the way they'd always done it, and then they did 8 wells in 2023 using the formulation and got the results that we predicted.
And I didn't bring that up in the talk because it's not EOR, but we're seeing a big growth in our business in completion fluid optimization.
Dr. Thyne, I work for EORI, just joined EORI, okay? Now, my question, I also worked on the Pluto way, low salinity field, okay?
Oh, yeah.
And so,
Caparic.
no, Pluto.
Well, yeah, but the low self-flow was in Caparic, right?
Okay. So now my question is that when we talk of low salinity, and your two thesis based on wettability, okay? Wettability, because of the production and injection history, it changes quite a lot. So on our interval patterns of 14 million feet, it works good. But beyond that, if we don't understand very well, and we have seen we took a lot of samples from Pluto Bay, analyzed it from one pattern to a neighboring pattern, it changes. So your ESal, I mean, does it engineer water pattern to pattern, or it just use the combined umbrella of the whole field? And that's where my worry is, you know, because many of the fields, okay, in Wyoming, we got fossils and medicine water. But in many of the fields, you have to set up a reverse osmosis plant, right, which can be very expensive. And so again, the question is, how do you account for the variability and wettability from one pattern to another? The second question is, have you looked at the calcium and magnesium production of produced water?
Yes.
That should give you a very good indication of whether the low saline is working or not, because typically we are looking at 90% water cut feed with already 90% water cut. We are looking at only 2 to 3% increase in production, and that can be difficult to measure. So any
I think
So the question is, what do you do? How do you handle when wettability changes across the field?
exactly. So when you say product-based water wet, yeah, in the native state it was all wet or water wet, but due to continuous production injection, the wettability is changed over time.
so. If I understand the question right, you're suggesting two things. One is that there's a natural variability in across a field in wettability right from the start.
Yep.
Remember, we're testing as many tests as you want to pay for. So if you believe that you actually have some variation, and this is where you have to sit down with the geologists and the engineers that are working the field. What are you seeing in the field production? What kind of variability are you seeing, and what are you tying it to? Do you want to test one facies, two facies, three facies? Do you think they're facies? Do you think there's an actual wettability facies? I haven't seen that data anywhere from anybody. Wettability testing is slow and expensive, so you just don't see big data sets. We have by far the biggest data set. We have not seen that specific problem. And we could talk about this offline, because I think there's a reason for those results from Prudhoe. I have talked with some of the guys up there, and I worked Prudhoe for a while. I think that you have to decide, in a practical sense, what's my flow unit in the reservoir? What am I flooding? That's the thing I want to affect. And by having a range of salinities, we're able to accommodate that, if you will, in the plan for execution. Second question was calcium, magnesium, I think, right? Um,
Was that in the produced water or the injection water?
Produced water.
Okay,
can I
So
talk
you
about
measure
that?
The calcium, magnesium content of produced
Okay.
water, and then you determine.
It turns out that I have to be careful.
got the approval, now he's all
My attorney,
excited.
right? It's the sodium to divalent ratio
Right.
that's a lever, a smaller knob. So the big knob is salinity, and then, it's like with the old radios, you got smaller knobs. Smaller knob would be the monovalent to divalent cation ratio. And that's a knob that you can use to further change wettability outside of the overall salinity. So there's a couple levels of knobs, if you will, in this process, in this technology. And we could talk about that in more detail because I have permission.
And the last question, and okay, Dr. Thyne, I was reading your report, okay, when you're working for EORI on low sensitive certain mineral use, okay.
Yep.
And what I found is that the fields in the, and I started this part yesterday, the field in the northeast part of the mineral use, okay, there are 10 million very small contained fields with 90% water cut. So why not try it there?
Okay, so we have to go, the question is, why didn't we do the Minaloosa, basically, right? We have to go back when Lon and I were working together at the Institute way back then. And the first thing we tried was the Minaloosa. And that was because Peter Wohl and Ron Surdam cornered me at a party one night and said, hey, they've flooded the heck out of the Minaloosa with all different kinds of water. You should check there first. So we checked 50 fields. It made no difference. And the director told me, you're useless. Was not Lon, by the way. Who
It
said
was
that.
you.
Yeah. It was discouraging. And Vicky Stamp called me up, who was a commissioner then, and said, well, why didn't it work in the Minaloosa? And that bugged me. And so I took 6 months and figured out why. And
Which one do you want?
let's see if we can,
Which one do you want?
the how to screen.
Oh, is that in yours or mine?
Oh, it's in yours. It's in both. I think that is definitely in yours.
There. Is
Ah,
that it?
rock. I just labeled it rock. It's clay. What does the Minaloosa not have? Clay.
Yesterday there came.
It's crazy. The Minaloosa is the cleanest freaking sandstone. You'd think it's perfect. No, it doesn't have clay. If you don't have clay, you don't get leverage in this. So if we're talking Wyoming, muddy, just list them out. Even the Nugget has clay, but not the Minaloosa. Any other questions?
Well, comment, Arco and Amico published paper that made good work by good men as they went through the reuse field and the afterthoughts that were there. I did not see studying virtually all of their papers. Years later, I did not see the fine look at ionic chemistry in their papers. It wasn't a thought process in most of the papers, not being critical, because it was excellent work, but it didn't deal with this.
You're correct, as I worked at Arco at one time. And
That's why the question.
right, I found, so the question is, why didn't anybody see this? I remember Jake Rathmel, everybody worked on Prudhoe Bay at the time. And he did the wettability measurements. And he did them with core flooding. And he got neutral wettability in the Salinity interval in Prudhoe Bay. But that kind of, we went right into the gas injection program. And so they thought all this great production was gas injection, and it definitely was a piece of it. But they had a naturally neutral wet reservoir. So they're over 55, 60% now in that particular interval. I think what happened was it just never occurred to somebody that salinity would change wettability because they didn't know, well, they knew about speckled wettability, but it was a very academic thing. No one thought it was something you could manipulate. And it turns out it is. So I think this is a big thing in the oil industry moving forward.
Right.
Because I think EOR is the oil, okay? My soapbox, the oil industry moving forward is going to be more and more EOR and less exploration and discovery, just because we've drilled every place but Antarctica. And we're moving offshore, and there are limits, economic limits. That barrel costs more money when you're offshore.
You guys talk to, EORI and, one of the Phillips, they're good to operate.
I have talked to Hillcorp. They've been difficult to penetrate. I believe, honestly now, I believe Hillcorp, Exxon, ConocoPhillips, which we did pretty well. We got to vice president, not bad. All these companies will be second. The small companies in places like Wyoming who can get things done will be first. And everybody will be sitting there going, oh, because we all know new tech, we all love new tech if we're second. We don't want to be the first guy with new tech because something might go wrong. So I honestly believe this is what's going to happen. And Wyoming is the place because of the variation we have in reservoirs, the types, the temperatures. We have all these different features here. And we have lots of, as you said, old water floods at 90, 95% water cut. So what do you have to risk? I mean, we're not going to get paid if it doesn't work.
And industry is going to become more aware of how important water quality and the water chemistry is of their injection fluids, their completion fluids. And so, yeah.
One of the things that highlight both micrographs, right there, all you see detailed work on clays. I mean, the whole clay series, hillites, water sensitivity, mistakes that were made using freshwater foxholes is gone, pulling foxhole water into the reservoir, just locking up the reservoir.
The muddy, oh Lord, yes. And this is one of the pieces of our process. We can come up with a great salinity for your reservoir. If it's going to cause formation damage, it doesn't work.
Right.
So fortunately, all that work, and this is really where LoSal started, was observation and formation damage. And one guy in 67 noticed it got better with fresh water. And that kind of languished until Norm Morrow came to the University of Wyoming and picked up that idea. And that's low salinity water flooding was the big thing. And what happened was low salinity water flooding, when it works, great. When it doesn't work, bad. And so the whole idea of this when we were working together at the Institute was, can we find something that's predictable and cheap and robust? And so that's been the goals, developing this technology, focused just on that. And may I say, Tom Strook's vision, you know, let's go back all the way. He said, we produce 7 billion barrels in this state, roughly at this point, which means we probably have 21 billion barrels. So how do we get a few more? And we all know CO2 will work, but it's expensive. I think Lon put up a sheet last year, 400 million a project for CapEx, something like that. And it's just, that's intimidating. I can't raise that money. No one can raise that money. Gradually you do. and you see what happened to Beaver Creek, for instance, that's a long-term project. They're only flooding one zone right now with CO2. But CO2 is a long play and it's expensive play. This is not.
Well, you could use this in the meantime,
Yeah,
flood your field with, ESal injection water and then get the capital, the money to pay for the CO2 infrastructure.
yeah, and the corrosion and
Yeah.
dealing. It was
CO2
not
is somebody
cheap.
else's problem.
Yeah, it was not cheap to do Beaver Creek. Talking to some of the people that work there, they had to pull a lot of pipe.
In earlier years, teaching Venezuela, places in the world. Treated the hand of it, shoulders. As to what was going on, Maryland, corporate, and all that changed. But you don't see the opportunity that might exist because clay exists. The whole point of a lot of the work that was done by larger entities who were well capitalized, who rolled into the recluse field, and everybody presumably knows the stories and the rest of that. We're disenchanted with the clays that existed there. You're proposing that they're possibly a resource. There's a lot of oil locked up in it.
Yep.
There's been a lot of discussion in the Institute over the years, I think the feeds and the rest, about all the oil that is still in place there. But you need a way to unlock it. It's the economic.
Yeah, I think, so the comment is really, that graph says that having a bunch of clay in your field might not be a bad thing for this technology.
It was a bad thing for everyone who's come before.
And I think your comment about standing on the shoulders is well taken. Most of this came out of the literature. People, one project at a time here and there, have laid the groundwork for this. What we did was, because Teresa could get the funding, we could sit there and do 5,000 experiments where we only varied one thing at a time. Just the rock type, just the amount of sodium to calcium. We went all the way back just to doing sodium chloride stuff. So we're able to build this huge piece of information, the matrix, as we call it. And then you know what you do with the matrix. You have fun. You analyze it, you figure out what the drivers are. And so that was really, it's all been there. The problem was everything was isolated projects by all these great people who then, if you worked at an oil company, you moved on to the next project. You weren't going to spend your career doing one thing.
Exactly. Story.
Yeah,
Mhm.
and so we've seen that. We see that in the literature. I think I've got over 500 papers now of literature stuff that goes into this matrix, drawn from things. It's interesting that you can't, I'll put it this way, the large commercial databases of production data are very useful if you're looking for breaks in slope. So you have a well-established decline rate in a field on water flood, and you'll see a break in slope. The few people I get to talk to who know anything about it say, oh yeah, we changed water chemistry injecting there. And you're like, oh. So, there are a lot of clues out there in people's production data that shows sometimes this happens and sometimes you get a benefit and the engineer takes full credit, right? Always. And then if you get the red one, it's the geologist's fault. That's usually how it works. Sorry, I'm cynical.
And you're very right about that. That clip, I mean, to 1,000 that's just we did and under single with chemical test. Clay is very, very important.
Yeah, so clay is good sometimes.
On purpose, smile.
Yeah, what you don't want is too much smectite, right? Because that'll swell. So you don't want the swelling clays and you don't want the clays that'll detach into fines.
That's bad news.
Yeah.
It comes with
Hmm.
It does, and so, you know, you work the best you can. It's just another tool in the toolbox. That's what I always say to the engineers. They say, hey, I got a new tool for you. Because we all love tools. Any other questions then? Well, then, we'll be here a little longer for if you want to sit down and just chat. But thank you so much
Thank
for
you.
having us today.
Appreciate it.
Well, I'd certainly like to thank Teresa and Dr. Thyne for their time and presentation today. I'd also like to say that if there's any interest, please reach out to the folks at ESal or contact the Enhanced Oil Recovery Institute. I'd also like to make note that our next EORI Insights is going to be February 11th, and it'll be titled BioSqueeze. So again, thank you all for your time and attendance today.